Good morning to all. We welcome you all to the 2 weeks online FDP on advances in composite materials, manufacturing processes, and optimization techniques. This is 8th day of FDP. Today we have two interesting sessions. The first one from Dr.N.Senthilkumar sir, Professor, Savita University, on machining of composites. Already we had two interesting sessions from him. Hence, I think no introduction is needed here. Now, I would like to invite Dr. N.Senthilkumar sir to address the gathering. Sir, please, sir.
So, good morning, Professor Dr. Senthilkumar sir and Dr. Vijayakant sir. First and foremost, I have to thank you all and Dr. R. Karthikeyan sir for this opportunity. And so far, we have seen two sessions. One is on a simulation of machining processes, and second one is Taguchi's DOE with the hands-on training using Minitab software. And today, we are going to see a little bit different topics apart from this, because so far what we have done is we have seen many of them doing the same things. But the machining of composites is very, very important topic, because nowadays most of the research works are focused on composite materials. It may be synthesis, different methods of synthesis in composites, then characterization techniques. Apart from mechanical properties, we will be studying the wear properties using pin on disc or three body operation, or we will be carrying out the corrosion behavior. The corrosion behavior we will be doing with salt spray test or impedance spectroscopy. Okay, so likewise there are many characterization techniques available, and apart from this fatigue test we will be doing, okay, creep test they will be doing, right, then forming and then machining. Because whatever material that we are going to produce, it will be only the near net shape. It will be only in the near net shape. That is, it is not as accurate as we need. That's why we use the term near net shape. Because if I want to produce any component, okay, from the bulk material we have to reduce it to the shape. But with the usage of composites or casting process, even the alloys, can be made to the near net shapes. So the difference, the difference between the alloys and the composites is, alloys is made up of two different materials. When it is being added together, it reacts and forms intermetallic compounds. For example, iron and carbon. These two are separate. When I am going to add these two, it becomes steel. And the formation of iron carbide. So it becomes an alloy of iron and carbon. But this is contrary to the formation of composites. If I am going to add two materials, the two materials will be as it is. There is no intermetallic compounds. So when I am going to add aluminum alloy and any ceramic or even fibers, the fibers may be synthetic fibers or it may be the natural fibers, whatever it is. If I am going to add this alloy, not only aluminum alloy, we can also use magnesium alloys, okay, or whatever material we like, according to the application. Application and purpose is very, very essential in deciding what kind of material that we are going to produce or fabricate, for what application we are going to use. So based on that only we have to select the base material and the reinforcing phases, right? For example, if I am going to consider aluminum alloy 6061 as my base material and a ceramic reinforcement SiC, silicon carbide. So when I am going to combine these two, when I am going to reinforce SiC with aluminum alloy, SiC will remain as SiC. And that's the beauty of the composite material, because it won't react with the aluminum alloy elements. Elemental compositions it is going to have. It won't react with it. Then what is the main thing of fabricating these composites? We have some advantages of aluminum alloy. We have some advantages of SiC. Both of these has disadvantages and limitations also. So the advantage of one will compensate the limitation of the other. So the advantage of going with aluminum or magnesium alloy is lightweight, but the limitation is less strength. While we are going to take into the part of reinforcement, it produces high strength. That's high strength, right? So the less strength of the aluminum is compensated by adding the reinforcement phases, which are going to be high in strength. So lightweight, high strength materials can be obtained by using composites. So there are different manufacturing procedures of doing this. Okay, composites is not only the metal matrix composite, we have a polymer matrix composites, we have ceramic matrix composites. So different matrix composites are there, and different reinforcement phases is also there. You can go with the short fibers, viscous, long fibers. Then we'll go with the ceramic reinforcements. In the ceramic reinforcements also, we can have the micro size, we can also have the nano size. So depending upon this, many fabrication methods are there. Okay, but the most economical method of fabricating the metal matrix composite is strip casting technique. If I'm going with the nano, and for a dispersion of the particulates, we'll be going on with the ultrasonic cavitation methods. So we have fabricated the material, and then we are going for the characterization studies. The characterization studies will be going on with the first thing that what we have to do is the distribution of particulates inside the matrix. Okay, if the particulate distribution is even or uniform, then we can attain very good properties. If it is agglomerated, if the particles get attached and it is not evenly distributed, then the property of the composite will not be that much good enough. That's what we require. So first and foremost thing that we have to see is the micrographs, whether it may be the optical or it may be the scanning electron microscope. So whatever it is, okay. Then going on to the tensile test. Then from the tensile test, we can move on to the hardness, then compression, then impact. Okay, then flexural. There are many tests that are available. Okay, these are all the basics that what we will be mainly doing. But once coming back to the machinability studies, okay, these composites behave in a different manner. That's where the complication exists. Why? Because these are all generalized methods which we are going to do as per the ASTM standards to characterize the materials. So we are going to follow the ASTM standards only for each and every test. Okay. They are
Sir,
not.
excuse me, sir.
Yes.
Sir, you are speaking with the first slide or
Yes. I'm speaking with it because I'm giving some of the introduction about that. Okay. So coming on to the machinability aspects, okay, the main thing, now it is visible?
Yeah, sir.
Okay. So speaking on to the materials, so we have been evolved from many materials and now towards the advanced composites. So you can see before Christ itself, we have these composites. So this composite is not a new thing, whatever we think. So nowadays only we are going to fabricate these composites and then we are going to use it in a different aspects in aerospace, automotive, no, defense, no. So dating back to 10,000 before Christ, we have these polymers, okay, we have these composites, we have the ceramics. So most of the paintings in that era, you can see nanoparticles being included in that. So that is a very big topic. So all these things is not new. So now we have sophisticated methods of fabricating composites. So we know it very well. But the first set of composite materials is the straw and brick. For building houses, they use. So in countrysides also they will be using the straws mixed with the mud. You can see. So that it becomes very hard enough. Okay. So the properties becomes higher. So now you can see the usage of this tends to lower in 1960s, and above which you can see the drastic development of these polymers and then composites. Right? The polymers and elastomers along with the composites also we can take it. Okay. So, but the usage of the metals is very, very higher. Okay, but we are not going with the traditional materials. We are going with the high performance materials nowadays for usage in aerospace, defense, and automotive applications. And their main aim is to reduce the weight. So, weight to strength ratio has to be very, very high, right? So, this is how the different materials has evolved over a period of time. So, now coming on to the composites. So the composites of two types, general types is of two types. One is general composite and the other one is the hybrid composite or mono composites or hybrid composites. So what is the difference between mono composites and hybrid composites? If I'm going to have only one reinforcement, then we call it as a mono composite. If I'm going to have two reinforcement, a primary reinforcement and the secondary reinforcement, then we call it as a hybrid composite. Nowadays we can also have ternary effects also, ternary reinforcements. That is addition of third component. Ternary, we call it as ternary. Okay. So what is the main purpose of adding secondary reinforcements? So that will come into your mind. So I'm going to add a ceramic reinforcement as the primary reinforcement. With this, if I'm going to use that materials in a brake drum, for example, I'm going to use it in a brake drum of an automobile. It's very, very hard material, no? So the brake drum and all, there will be high amount of frictions. If there is high amount of frictions, the wear will be higher. So in that cases, if I want to reduce the friction, then some sort of lubricants has to be added. So for this purpose, during the fabrication method itself, we will be adding some amount of solid lubricants. We will add some amount of solid lubricants. Okay. So which will assist in reducing the friction between the sliding surfaces. So there are different types of solid lubricants. The most important of that is the graphite, right? Then molybdenum disulfide we will be having. Then nowadays we are going to use mica. Mica is also a solid lubricant which also produces good properties. Okay. So coming down to this, so we have the metals. So steels, cast iron, aluminum alloys, copper alloys. So these are all called as metals because it forms intermetallic components. Then we have the polymers, right? Polyethylene, polypropylene. Okay. Then PEEK, polyacetylene. Okay, whatever it is, epoxy. Epoxy we will be using mostly for the formation of composites. Okay. Then we have the glasses, glass fibers, borosilicate glasses in micron size, in nano sizes. Then we have the glass fiber. Okay, silica glasses. Then elastomers, butyl rubbers. So nowadays we are going to we are also going to have a good research amount of research in this elastomers also, because these elastomers are mainly used at a high temperature application. For example, look at a gasket or a washer. So that's why we will be consistently telling for what kind of application you are going to produce that composite. That is very, very important. So these elastomers are specifically useful for producing gaskets and washers that can be used in high temperature applications. So for this, what type of reinforcements has to be used so that its property will be enhanced? Then we have the ceramics. Alumina, silicon carbide, silicon nitride, zirconium oxides there. Okay, silicon nitrides. There are many things. Boron carbides, boron nitride. Okay, there are many different types of ceramics, both in the micron size as well as in the nano size. So what is the main difference of micron and nano? So if the range of size of any particles is 1 to 100 nanometer, then only it will be called as nano. So 1 to 100 nanometer, up to 99 nanometer, 100 nanometer, we'll call it as a nano size. 110 nanometer, the size of the particle is 110 nanometer. We should not call it as nano. We should call it as only micro. So within the range of 1 to 100 nanometers, the particles will be called as nanomaterials. If it crosses that 100 nanometer range, then it will be classified under the micron sized particulates only. So this is the main difference. And one more thing is, whenever we are going to cut down the sizes to nanoscale level, the surface area will be higher. The surface area will be higher, which because of that, even with a little amount of nanoparticle additions, a substantial increase in properties can be observed. A substantial increase in properties can be observed. So that is the main advantage of going with the nano. But the problem is the economical aspect. The cost of the nanomaterials is very, very higher. So we have to have a trade-off between the properties and the cost that is being associated. Okay. Then this is the relationship that exists between the Young's modulus and the fracture toughness of different materials. So here we can have the different matrix materials, different reinforcing phases. Okay. Like this. So based on this, we can select materials. Based on this, we can select materials. So here I am going with the ceramics, for example. The ceramics have high Young's modulus, but it has a moderate or a lower fracture toughness. So here you can see the aluminum oxide, silicon nitride, silicon carbide, tungsten carbide. Tungsten carbide are mostly used in cutting tools. Tungsten carbides are mostly used in cutting tools. Okay. So now coming on to the titanium alloys, you can see the titanium alloys, copper alloys, nickel alloys. So nickel, titanium are mostly used in the aerospace industries because it has higher Young's modulus and higher fracture toughness. So titanium alloys, nickel alloys. Okay, then tungsten alloys also we have. Okay, it has higher Young's modulus and higher fracture toughness. Right? So based on this only we have to select what type of material that we are going to choose. Right? What type of matrix material we are going to. So here you can see zinc alloys, the magnesium alloys, aluminum alloys. Right? So when compared to that of magnesium alloys, these aluminum alloys are higher in Young's modulus and also in fracture toughness. Then what is the reason magnesium is preferred over aluminum? Because of its lightweight. Because of its lightweight. But the only drawback is during fabrication, it will catch fire. Right? So we should have a environment which suppresses that fire behavior of the magnesium alloys. So here, based on these elastomers, you can have the polymers. You can have, okay, these are the elastomers. So based on this only we can select. Based on this only we can select. So this is a general material selection guide. Okay, so based on which we can select the different materials for our applications. So this what we will be insisting again and again and again. So just selecting two materials, mixing it up, developing a composite won't produce a novelty. Novelty and the application side also it will be very, very tough to find an application. But go with an application, select an appropriate material for that, fabricate, then only we can have a very good material for your research work. Then these are the general classification of composites. So we have the different depending upon the matrix phase and the reinforcement phases. Okay, so polymer, metal, and then ceramic. This and all you know it very well because for the past 10 days you are seeing this only. So again, I don't want to confuse you. So I'll be skipping this. Now coming on to the machining. So this is the main theme of today's presentation. So far what we have seen is what is meant by composite, what is the need of this, what are the various characterizations that normally we will do. So we have to be different from other people's. So normally they will be doing only the characterizations. So apart from characterizations, we have to do some machining process. Then only we can be able to do little bit of something different from the regular people. Right. So what is meant by machining? So machining is a manufacturing process. Machining is a manufacturing process. What it actually does, it removes material. Why we have to remove material? Because we want to convert the raw material into a finished component. For this, some amount of material has to be removed. The material that is to be removed is an unwanted material, and that can be usually removed as chips. So this is the normal definition of any machining process. So removal of unwanted material by means of chips, by using a sharp cutting tool, by using a sharp cutting tool. Okay. So even though we are going to produce, so this is the first point that I have told during the introduction part. So whatever things that we are going to do to form a product, we will be doing forming or we will be doing forging, whatever it is, we can produce components only to the near net shape. That is, for example, I want a shaft. Its dimension should be 10 mm. The 10 mm shaft I am going to produce, but exactly 10 mm I should not produce. Okay, because the surface roughness, everything, there will be some some surface cracks onto this. Okay, some scalings will be there, so that has to be removed. Okay, so for this, what we will do is near net shape. Instead of 10 mm, I will be producing it to 12 mm, and that 2 mm I will be removing. So for that purpose only, we will be using that machining process. So what happens when I am going to remove from another block, a raw material of 20 mm? If I want to reduce it from the 20 mm to 10 mm, then 10 mm of material will be wasted. Because once the material is removed as chip, it is a scrap. We cannot reuse that. So once again, it has to be given back to the casting. Okay, we have to cast it into desired billets. Okay, so even though we convert this into near net shapes, machining is required. We cannot omit any machining process, right? So this machining process consists of dependent and independent variables. That is what we are speaking for the past two sessions. So dependent variables are the outputs and the independent variables are the inputs, right? And also there is some relationship that exists between the inputs and the outputs. So that is what we have seen in the machining simulation also, and also on the Taguchi's hands-on training also with some examples. So there will be some relationship because increasing the value of one input will have an effect on the output, whether it will increase or decrease. So that's the case. So during machining process, we have different input parameters. So the workpiece parameters, then cutting tool parameters, cutting parameters, so different. So it be specific in this. So cutting tool parameter is different and cutting parameters is different than experimental design. So in machining, the workpiece that what you are going to select will be of much importance. Whether we are going to select a lightweight alloy, a composite, or high strength materials, or die steel. So there are different materials that we can select as a base material. If it is a soft material, then we can use the HSS for machining. If it is a very hard material like die steels, then we have to go with the cemented carbides or polycrystalline boron PCBN or CBN or PCD, whatever it is. So different cutting tools has to be used. So workpiece parameters, the hardness. Okay. Then cutting tool parameters. What is the use of cutting tool parameters? If I'm going to choose a cutting tool, then the first parameter that we will be looking is the nose radius. What is the nose radius of the cutting tool? Second, what is the relief angle? What is the cutting edge angle? What is the approach angle? So this only limited I am telling, but there are many things. If I'm going with the drilling, then what is the helix angle? Then what is the point angle? How many flutes are there? What is the diameter of the cutting tool? So these are different parameters that exist in a cutting tool parameters. Then cutting parameters, machining, cutting speed, feed rate, depth of cut. Okay, then the type of cooling that what we are going to use. So these are the cutting parameters. And experimental design, whether we are going with a trial and error approach, single factorial design, full factorial design, then any specialized design of experiments, that on top. So based on these inputs, I am going to do the machining process and then I am going to identify the outputs, and from the outputs what you are going to find. So that's our ultimate aim. That's our ultimate aim. Okay, in this presentation also we are going to determine what makes what. Okay. by using these kinds of materials, by machining these materials with this, what is the effect? So that and all we will be looking at later on. So the machinability. What is by machinability? It is the ease with which a material can be machined. The ease with which a metal can be machined is known as machinability. So it all depends on three important factors. So everyone will be looking on to only two factors. One is the matrix material and the other one is the reinforcement material. But the one more important thing or aspect is this interface bond characteristics. How the interface is interface bonding. Because if the particulates that what we are going to add, if it is going to be in the middle of the grains, then it is well and good. If it is on the grain boundaries, then the properties will be enhanced because it blocks the dislocation movements and shearing actions also it will restrict. So what is the interface bond that exists between these particulates and the matrix alloy? So that is one of the important aspects in machining, right? So the reinforcement phases depends on the type, the chemical composition, SiC, B4C, TiC, TiO2, Bn, Si3N4, WC. So what's the chemical composition and what is its corresponding hardness? So that's very, very important. Then we have the shape, whether it is the micron shaped or whether it is the nano shaped. Okay, whether it is particulates or whether it is viscous. Okay, whether it is fiber or what it is. Okay, then size. How much size? 40 microns, 80 microns, 120 microns, 60 nanometers. So the size, volume fractions, whether I am going to put it in 5% of volume or weight, 10, 15, 20, 30, 35, likewise. Right? So how much of reinforcement that we are going to add? How the distribution is made inside the matrix. So this is very, 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 very important aspect. How it is being distributed. That's why during the introduction part of the composites, machining itself, the composites itself, I told the first thing that we have to do after performing the fabrication process is looking at its microstructure, because how the reinforcement particles are being distributed. So based on the distribution only, the strength of the composite and also the machinability behavior of the composite will be predicted a little bit. Okay, if it is getting agglomerated means then there is a drastic change in behavior. Okay, so uniform distribution is needed in all the cases. Okay, then we move on to the matrix material. What is the composition of alloy? AA 2014, aluminum alloy 2014, aluminum alloy 6061, aluminum alloy 6063, aluminum alloy 7075, LM25. So these are the different aluminum alloys that we will be considering. So each and every compositions are series. You can see 2 series, 3 series, 6 series, 7 series, 8 series. Some special alloying elements will be added to improve its properties. Right? Then the microstructure. What kind of microstructure that we are going to have? Because in some cases, after fabricating the composites also, there will be heat treating. And then there will be precipitate hardening. They will be doing the precipitate hardening. So in that cases, the machinability index will be further reduced. So it becomes more tough to machine that. Then strain hardening solutions. So this is also one of the important things. You can see less number of papers in strain hardening effects because it requires a special addressing and all. So you can have a very good research paper on the strain hardening characteristics. Okay. So the machinability mainly depends upon, right, the properties of all materials, that is the reinforcing phases and also the matrix phases, okay, which influence the machining process. Not only that materials, but also what kind of cutting tool that you are going to select. Whether you are going with a high-speed steel or we are going with the cemented carbide or we are going with any specialized cutting tools. So their compositions, their hot hardness. So in cutting tools, we will be coming across this word hot hardness, that is regaining hardness at high temperatures, regaining hardness at high temperatures. Because whenever we are going to machine these composites, the temperature of the interfaces will be really high than that of alloy materials. So in that cases, the cutting tools should retain their hardness at a higher temperature. So, and also it should be able to withstand that sharpness, the cutting edge, sharpness of the cutting edge. That's why we are going with the cubic boron nitride or polycrystalline diamond. Okay. So it all depends on the material properties. Then we are going to have a relationship between the what type of process employed. Whether it is the turning process, whether it is the drilling process, whether it is the milling process, the tool material, that's what we have seen, HSS or tungsten carbide or polycrystalline diamond, cubic boron nitride, and the cutting parameters that what you are going to choose. Cutting parameters means normally we will be considering the cutting speed, feed rate, depth of cut in case of turning. In case of drilling, rotational speed of drill and then feed rate we will be considering. Only two parameters we can consider in drilling. In case of milling, we can consider cutting speed, feed rate, and depth of cut. What is the value that you are going to consider? Because for during composite machining, we cannot consider high cutting speeds because chipping of tool will occur. Because there will be soft matrix, suddenly a reinforcement phase will be coming in contact with the cutting tool. So that's the problem in composite. Okay, are you able to understand? While the machining, the soft metal matrix, it will be easy for the cutting tool to remove. But suddenly, if a reinforcement particles, a boron carbide or a boron nitride is going to be in contact with the cutting tool, because of that high speed, chipping of tool will occur. So, yes, low speed or a moderate speed is recommended for machining. Okay. So, in order to assess the machinability, because the purpose of doing the studies, research work on machining of composites is to determine its machinability. Okay, how this machinability is assessed? So we have to have some assessment, no, in determining that machinability. So in that category, we will be having the first thing is the tool life. Then we have the cutting forces. Then we have the surface finish. Then chip formations. So this is the condition what you have seen in the simulation studies also. Earlier simulation studies were focused only on the tool wear. Later nowadays we are going to incorporate the surface deformations, the surface irregularities, then chip formations, then cutting forces, then strain hardening coefficients, everything we are going to study. Similarly, the importance of the machining of composites is we are going to assess the machinability by considering tool life. Cutting forces is very, very essential. Then chip formation, because whenever we are going to use a high speed, then built-up chips will be formed. In most of the cases, you can see only segmented chips will be there. Most of the cases, we can see segmented chips. Okay, because continuous chips will be available with some ductile materials as base material, as the matrix material. If I'm going to have some ductile materials as a matrix material, then continuous chips can be observed. There. So depending on the properties of both the reinforcement phases, matrix phases and cutting tool materials, wide difference in machinability of different materials will be there. Right? For example, I'm going to have two different composites. AA6061 plus 5% SiC. AA6061 plus 10% SiC. Whether the two machinability indexes will be the same? No, because higher amount of reinforcing phases are there in these 10%. The mechanical properties will tend to change. The interface bonding strength will tend to change. So different materials have different machinability indexes. So this is the metal cutting mechanism that everyone knows. Okay. So this is the primary deformation zone, and this is the secondary deformation zone, and this is the shear zone, and this is the shear plane angles, So this is the chip, the tool. So the chip is removed as the Pispanian model. So this is what we are calling as the Pispanian model. So the layer by layer, the material will be removed. That is card, stack of cards. In playing cards, no, we have playing cards. The playing cards will be keeping one card over another card. If I remove first card, then I will remove second card, third card, fourth card. So layer by layer, the material is removed. That's why stack of cards. We call it as this stack of cards. This is given by Pispanian. That's why this is called as a Pispanian model of chip formation. Okay. So these are the cutting forces that is going to act on the tool and on the workpieces. Okay. So this is the generalized one of metal cutting mechanisms, right? So even the cutting forces, the shearing actions, the chip formation, so everything is being given in one frame. Okay. So for what purpose we have to go with the machining of composites? So there should be some need, no? First thing is improving the machining possibilities of the composite, because even though we are going to produce castings that is similar to that of the final component, the exact dimensions will not be there. It will be near net shape only. So the machining is compulsory in that cases. We cannot omit machining. Second, we are going to provide a cutting data. So you can see many handbooks, machining handbooks, cutting tool handbooks. In that, even in Vidya, you can see Vidya, Sandvik. These are the two popular cutting tools makers. So Vidya also they will give for a specific uncoated carbide insert of a specific shape nomenclature. They will be providing the range of cutting speed, the range of feed rate, and range of depth of cut. How they have formulated them? So that can be formulated based on the machining of materials. For different materials, so they will be giving for low carbon steel, high carbon steel, medium carbon steel, for cast iron. So everything they will be giving the data. On what aspects? So they have the cutting tool data are to be produced. So for this, the machining of composites is very, very useful. Why we want to have a standard data? Because designers, okay, if I want to convince a designer in choosing this particular material, then they should know. So this material is machinable. After fabricating, if the composite material is not machinable, then whatever effort that is being put is of waste. Am I right or wrong? So I have fabricated a composite, a very good composite with good mechanical properties, but the machining is not possible. The material is not being removed even with the advanced materials, advanced cutting tools. What happens? That material is a waste. Okay. So for these purposes, we need the machining of composites, right? So as previously told, by incorporating the reinforcing particulates in the MMC, their mechanical properties will be improved. Their mechanical properties will be improved. But during that machining process, even though we are going to have higher mechanical properties, but during machining, higher tool wear occurs. Right? If the tool is going to wear more, then what happens to the surface finish of the machined part? Of this surface machined. So the surface finish of this machined surface will be rough or it will be wavy. So in assembly and all, we want only a good quality surface. We will want only a good quality surface. So for this, what kind of cutting tool will produce a very good surface finish, that we have to identify, and we have to use that tool only for machining. Okay. So this is what, even though we are going with the near net shapes forming and modified castings, this machining process cannot be eliminated. Okay, this machining process cannot be eliminated in all fields. Okay, so we have to finally go with some machining process. So the problem that arises is the difficulties that is associated with the efficient machining. What is the efficient machining? easy removal of material from the workpieces. That is the efficient machining. And precision. Precision means exact good surface finish, exact dimensions at a lower time. Okay, so that is precision means dimension should be as required with the good surface finish. Okay, so because of this, the problems are associated with the precision and efficient machining. So the machining, so this is what we are speaking about, the property of the matrix material and the property of the reinforcement particles will have an impact on the machinability of the MMCs. Apart from this, the third important thing that affects the machinability of the composites are the interactions that exist between the two constituents. One is the matrix constituent and the other one is the reinforcement constituent. So the what type of interaction that is going to be there between them? Okay, that will decide. That is the bonding characteristics. The bonding characteristics we call it as. Right? If the bond is high, then the material removal will be tough. If the bond is less, then less mechanical properties, then it is very easy to remove the material. So if I want a superior mechanical property, then the machinability will be really tough. Okay, so interfacial bond affects both the quality and the tool wear. Because if I am going to have a higher interfacial bond, then the mechanical strength will be good. In that cases, it is really tough to remove material. In that cases, the tool wears high. The tool wear will be high. So if the tool wear is high, obviously the surface finish will be worst. The surface finish or the quality of the surface will be worst condition. So some sort of trade-off has to be maintained between them. And the very important aspect that we are seeing from again and again is the distribution of the reinforcement particles. So uniform distributions, that is homogeneity in distribution of reinforcement phases and its alignment, how it is being aligned. How it is being aligned. Whether it is being aligned in all directions or it is being aligned in one direction. So that and all will have a great effect. Okay. So this is related to the fibers. If I am going to add a carbon fiber or if I am going to add any natural fibers in epoxy materials and then if I am going to do a drilling process, how the fibers are aligned in transverse direction or in the longitudinal directions, that will affect the delamination. So in that cases, you can study the delamination effects also in drilling. Then the crystalline structure of the material, matrix. The crystallinity of the matrix material will also have an effect on the machinability of composites. Then coming on to the reinforcement phases, the reinforcements are hard ceramic particles which are abrasive in nature. For example, silicon carbide, it is an abrasive particle, right? And it is also anisotropic. Okay, then it becomes very, very tough for us to machine when compared to that machining a homogeneous, what is it? So that is what we are speaking about. The matrix material, the reinforcement phases. The matrix material, it will be even, so it is even. It is easier to remove the material. But once a reinforcement particle comes in contact with the cutting tool, it becomes differently. Right? So this results in the damage being introduced into the workpiece. Okay, because the particles will be pulled out, or the particles will be suppressed, or the particles will be sheared. These are the three cases that we will be seeing later on. Okay, when a cutting tool comes in contact with the reinforcement particulates, it wears more because of the high hardness and toughness of the ceramic particles. Because the ceramic particles are very hard and very tough. So when a cutting tool comes in contact with that, it becomes highly wear. Types of machining. Normally what we will be doing is wet machining, then dry machining. Wet machining is also flood machining. Then normally what we will be using by supplying coolants. In dry machining, we will not supply coolants. Then why we have to go with the dry machining? Dry machining is an alternative to grinding process, surface grinding process. The dry machining is just an what to say, a alternate to the grinding process. Then we have the minimum quantity lubrication. Then we have the mist cooling. Okay. Then we have the cryogenic machining. In cryogenic machining, we will be using liquid nitrogen or liquid carbon dioxide. So the kit is around 16,000 rupees. That is also available anywhere. So you can have a kit and then we can do the machining process. So setup and all will cost around 20,000 rupees for this cryogenic machining. Then we have hard machining. What is hard machining? Machining a hard workpieces. That's all. Machining hard workpieces is known as hard machining. And what should be the hardness of the workpieces? Greater than 45 HRC in Rockwell C scale. So the hardness of the material should be 45 HRC. So in Rockwell C scale, the hardness should be 45. Then we have hot machining. What is meant by hot? Hot means we are going to heat the workpiece and make it hot. So in that cases, it becomes soft. The material will become a little bit soft. Then it will be easier for the cutting tool to remove the material. In that case, a high quality surface can be produced. A high quality surface finish can be produced in hot machining. Then we have the micro machining, removing micron sized materials. Okay. Then we have nano machining. Okay, by using diamonds. By using diamonds, they will be doing the machining process and the nano material will be removed. Atom by atom it will be removed. Okay, then we will see some of the main studies on metal matrix as well as on the polymer matrix composites. First we will move on to the metal matrix composites. So first we have to look into the stress strain curve for MMC, because here we are going to shear off some material. Some material has to be removed or being fractured from the workpiece. Then only it can be removed. So first it has the elastic region, then microplastic region, then the plastic region comes, and finally only it will be fractured. So this is the case which exists in a small area where the cutting tool comes in contact with the composite material. So at the small places, this plasticity has to occur and finally the fracture has to occur. So kindly think of how much amount of stress and strains will be acting at that point. So the workpiece and the cutting tool should withstand that stresses. Okay, that's why the measuring of the normal pressure at that point and then the cutting forces at this particular point is very, very essential. Okay, that's why we have moved from tool wear in 1980s towards today we are going to deal with the tool wear, surface toughness, cutting forces. Okay, so many other things we are going to have. So during machining of composite, the material undergoes both the elastic as well as plastic deformation. So initially it will be elastic. So with the further stresses, provision of further stresses, it converts into a plastic deformation and finally it will be removed as strip because of fracture. There comes a situation where a particulate will be there. Because the cutting tool is going to be in contact with the workpiece at only a small area. If there is a reinforcement particle, SiC, for example, silicon carbide particle is there, what happens? There are two cases. One, the matrix is soft actually. So if the cutting tool comes in contact with the particulate, the cutting tool will push the particulate inside the soft matrix. Okay, how it is going to push? By means of compressive stress. By means of compressive stress, it will push it out. Second category, because of that, it will shear the cutting, the silicon carbide particle will be cut into two halves. So that is called as shearing of ceramic particles. Or third case, that ceramic particle will be totally pulled out from the soft matrix. So these are the three cases that is possible. One, because of the compressive stress, the ceramic particles will be pushed into the soft matrix. Second case, it will be pulled out. And third case, it will be broken, that is sheared off. These are the three categories that normally we experience in particulate reinforcements. Right? So these mechanisms that is encountered by the ceramic particles that what we are going to reinforce will depend on the deformation behavior that occurs during the cutting, during the machining. So how it is being deformed? What deformation mechanism is going to be there? Okay. So at a high values of strain rate, you know, change in dimension towards, everyone knows strain. What is strain? Change in dimension divided by original dimension. Strain rate with respect to time, how much it is going to change? The dimension is going to change, right? So at high values of strain rate, so the matrix material is very difficult to deform. So it will not deform at all at higher strains, right? So at that time, what happens? The particles tend to be sheared by the tool. So as I told, the particle will be sheared. So it will be made into two, right? Like breaking a coconut. It will be sheared off. So one part will be with the chip and the other part will be with the soft matrix. That is called as shearing. So this occurs at a higher values of strains. So what is that higher value of strains? How we are going to provide? Higher cutting speeds, higher feed rates. So at that case, the particulates will be sheared off by the cutting tool. So this is the three cases that what we are going to see. Okay. So the first one. Okay, this is the generalized thing. A generalized workpiece. These are the particulates that what we are going to have. This is the cutting tool. So you can see some amount of particulates will also be removed as the chip. So there comes a thing. First case, particle cut through. So this is the case. At higher values of strain rate, the particles will be sheared off. You can see here. Some amount of particle is here and some amount of particle is here. Some amount of particle is here and some amount of particle is here. That is, it is being sheared off. And second case, here you can see the particle is being pulled out. So a cavity is being formed here. You can see a cavity. You can see a cavity here. So the total particulate is removed in the chip. Is being removed in the chip. You can see here. The particulate is being pulled and it removes of the chip. Okay. So at our lower speeds and due to lower strains, the matrix is easier to deform. At lower speeds, that's what we are selling. At a higher strain means higher cutting speeds and feed rates. At a lower strain means lower speeds, the matrix is easier to deform, and so that the particles are easily pulled out or pushed into the material. So no shearing of particulates takes place like this. The particle will not be sheared. Only at a high strain rate, the particle will be sheared. At low strain rates, it will be pushed inside like this. It will be pushed inside like this, or it will be pulled out, So that is the case, right? So after the material passes beneath this tool, that is, as the tool slides over the cutting workpiece material, the shearing action takes place. After the tool moves, the workpiece will regain some amount of elasticity. What happens? Because it is under compressive stresses. Once the tool moves, what happens? Some sort of elastic recovery occurs. So that is the case. So just prior to shearing action, so because now consider the cutting tool is going to come in contact with the reinforcing phases, that is the ceramic particulates. Okay, now it is going to shear. Okay, three scenarios are going to occur. One, the reinforcement particles are above the cutting tool. Two, below the cutting tool. third along the cutting line. What happens? So three scenarios are there. One is above the cutting tool, and second below the cutting tool, and third along the line of cutting action. Right? If the particle is above or below the cutting loom, the cutting line is nothing but the machining line. So this is the line that you can see. So this is the machining line. Okay. This is the machining line. So this particulate is on the cutting line. These three particulates are on the cutting line. This is below the tool and this is above the tool. This is above the tool and this is below the tool. So these are the three scenarios that what you are seeing. If the particle is above or below the line, it will be pushed into the chip. If the particle is above the tool, it will be sent to the chips. It will be removed along with the chip. If it is below it will be below the machining surface. Right? But when the particle is located exactly at the cutting line, it will be either pulled out or it will be sheared off. There are only two cases. Above the cutting line, below the cutting line, no effect. If it is along the cutting line, two actions will be there. One, the cutting tool, the reinforcement ceramic will be sheared off into two halves, or it will be pulled out. That's all. Or it will be pulled out. Right? Then the deformation mechanisms mainly depends on the matrix deformation rate. So at how much rate the matrix is going to deform. Right? It all depends on which will decide the deformation mechanisms. So how the material will be, because at a higher strain rates, at lower strain rates, it has to be differentiated. Right? If the particle is being sheared off like this, so here you can see, if the particle is being sheared off like this, you can see a good surface will be formed. A good surface will be formed. Whenever it is being pulled out like this, what happens? A rough surface with the cavities will be formed. A rough surface with the cavities will be formed. Right? But these cavities will also assist in some cases where in surface-to-surface contact applications, like in a brake drum, the oils will go and get locked into the cavities. That cavities will be filled with oils which produce the necessary lubrications. So here in the same image you can see there is a particle pull-out. So this is a fractured particulates. You can see fractured particulates. Right? So this is particle pull-out and this is a fractured particulates. Okay. So what are the various cutting tools that we will be using for machining purposes? First one is PCD. PCDs are higher hardness materials and higher tool life, but the problem is high cost. Second, we will be going with the ceramics, high cutting speeds and low feed rates. So you can see higher hardness, everything is going to be hardness, but PCD is hardened than anything. Right? So ceramics or cermets, we call it as a cermets. Okay, we have high cutting speeds. Cemented carbides. In cemented carbides, we will be having tungsten carbide. It is made up of tungsten carbide and tantalum carbide and cobalt. The cobalt is used as a binder in that cases. The cobalt is used as a binder which binds these tungsten carbide particles and the tantalum carbide particles. Coated carbides. So these cemented carbides are uncoated. If I want some performance to be improved, then I can give the coating. In the simulation studies also, after defining the workpiece, the cutting tool, there is an option, coating. The coating may be a single coating or it may be a double coating. Whatever we require, we can provide. Whatever we require, we can provide. Then coming on to the tool life. So this is what we are going to measure, the dependent variables. So tool life, cutting forces. So how the tool life will be changed or is being influenced. So the tool life is influenced by this size. First one is this size and how much volume fraction that you are going to add into the matrix material. Right? And apart from this, what is my cutting speed? That is, If the cutting speed is higher enough, then higher tool wear will be there. If the cutting speed is less, then less wear will be occurring. Right? So how the tool wear is going to be there? So what is the mechanism that is behind the tool wear? 2-body and 3-body abrasion mechanisms. Okay. Then apart from this, pitting. Okay. Pitting is nothing but because of the shearing action, the temperature of the tool will be higher. So which in terms comes in the in contact with the oxygens. So it becomes weaker. Then chipping. So you can see at the edges, the chipping is going to occur. Then fatigue. Because of the fatigue also, the chipping will be there. Right? So abrasion, because the chip is going to slide over the rack face of the cutting tool. Am I right? The chip is going to slide over the rack face of the cutting tool. If the chip has some hard particulates, it will make the rack face wear. So in secondary and primary flank faces, the wear will be there because of the abrasive action of these materials. Right? And even though the tool wear increases with speed, it also increases with the feed rate. Right? Higher feed rates will make higher stresses to be acting on the cutting tool. So obviously high wear rate will be there. Okay. Then cutting forces. The cutting speed has no influence on cutting forces. So only the feed rate will be influencing the cutting forces. But the cutting speed influences the tool wear. Cutting forces influences the tool wear. If there is high tool wear, then higher cutting forces will be there. That's a combinatory effect likewise. But the cutting forces are being influenced mainly by the feed rate and some amount by the depth of cut. So here you can see two images that we have provided. So this is the work that is done by some researchers. You can see with increase in feed rate, the cutting forces are going to increase in the same manner. Right? So similarly, the depth of cut, change in depth of cut, you can also see the cutting forces are going to be higher. In these cases, rather than that of feed rate, the depth of cut influence is higher. Because when the depth of cut increases, the amount of material removed will also be increasing. Am I right? When the depth of cut increases, the material removal rate increases. So which has a higher impact on the cutting forces generated. Because more material will be deformed. So that is the case. Then this is the drill wear with this depth of cut. Right? So this is for a composite material. So AA6061 plus 20% silicon carbide. So here you can see the flank wear is going to increase as the depth of cut is going to increase. How? Because when the depth of cut increases, higher material removal takes place. So in that cases, the wear and the cutting forces, both of them increases. And this is for drilling. Drill wear. This is the drill bit wear. So this is for drilling actually. Okay. So because we are going to have torque and thrust force are the two things that what we are going to have. So this is the relationship that exists between the two outputs. What is the influence of flank wear on torque? So you can see as the flank wear increases, the cutting forces increases. Are you able to see that? So increase in flank wear not only has an effect on tool, but also influences the torque. Okay, that is the rotational force. High amount of rotational force is needed because the cutting edges will become wear out. So high rotational speed is required in these cases. Okay, and also if the flank wear is higher, then obviously poor surface finish will be there. Poor surface will be produced. Okay. So this is by another person. Okay, from another one. So this is AL6061 plus 5% SiC composite. So spindle speed. So this is also drilling. So the tool rotational speed or spindle speed we call increases, the tool temperature increases. Here you can see on both the cases it is going to increase for different point angles. So what is the normal point angle that we will be considering in drilling is 118. The point angle normally we will consider in drilling is 118 degree. So if I am going to increase or decrease the point angle, then the tool temperatures and all these things will be getting increased. Okay, so you can see in both of the cases, the optimal point angle is going to be 118. Okay, but so by changing the point angle, you can see both the temperatures are being higher. So you can get a point how to measure the temperature. So there are two different types how we can measure the temperatures. One by using thermocouples. So you know the drill dia. So apart from this, you can put 4 or 8 small holes, and you can plant a thermocouple in that. You can plant a thermocouple, or you can use a non-contact type thermometer, infrared thermometers. So like what we are going to measure our temperature using a gun, thermometer gun, that what we are using for corona test to check our temperatures. So that is all 600, 300 rupees. But Metravi, that is one type of company that is producing these IR thermometers. Then Fluke, F-L-U-K-E, that is another company which is going to provide this for temperature analysis they will be producing. So it costs around 7,000 rupees, right? Up to 3 to 4 lakhs they are having this thermal analysis. Okay, so using that IR thermometers also you can measure these temperatures. But normally the contact type of thermocouples will be accepted in most of the cases. So this is the another category. So increase in feed rate. So this is the work that is done by Dr. Rajmohan and Dr. Panikma sir. So as the feed rate increases, okay, you can see the burr height increases with the higher weight percentage of silicon carbide. So he has changed this percentage of silicon carbide from 5% to 15%. So by increasing the feed rate, you can see with increase in silicon carbide content, the burr height increases. The burr height increases. Similarly, the surface roughness, it also increases, right? So there is a proportionality between the surface roughness and the burr height. So that is the cases. Okay. Then so far what you have seen is the conventional one. Now we are going for the non-conventional type machining process, EDM. So here you can see the current, pulse on time, pulse off time, then voltage, then servo feed. These are the different input parameters that what we will be considering in EDM, right? So when I am going to increase the current for different proportions, LM24 is the base material as cast, then I am going to add 1% silicon carbide, 3% and 5% silicon carbide. Now if I am going to study the material removal rate, you can see the material removal rate increases with the higher current. So for removing a higher material, I need higher currents. Okay, we need higher currents. And you can see with the higher currents, you can see this is one. Okay, if I'm going with the higher current, you can see the surface roughness will also be higher than that of the smaller currents. That is, if I'm going with the higher current, then obviously a higher material is removed. No, if a higher material is removed, then the surface finish will be bad. So this is also what it is going to have. Okay. Then this is for another one. Okay. This is aluminum metal matrix composite and the as cast one, right? So here the peak current increases, the surface roughness increases. So the same trend they are also going to have. So on time, pulse on time increases, surface roughness increases. The on time is the period for which the spark is provided. Pulse on time is the period for which the current is provided in EDM. Then pulse off time is the period for which the spark is not provided. The period for which, because alternately they have to provide pulse on time, off time, on time, off time. They have to give like that. Okay. So off time increases, the surface roughness decreases. Because only for limited period the pulse is there. So erosion takes place in that cases. Okay. Then electrochemical machining. Then electrochemical concentration with that of machining speed. With a higher concentration, higher erosion takes place. So machining speed will be higher. Right? But the overcut will be there. Because higher electrode means higher erosion is there. So higher overcut. Right? So this is the case for all these things. For voltage also we are going to have. This is the deformation factors. So this is for another thing. So you can have different parameters that affects the machinability behavior of composites. Not only in conventional, but also in non-traditional aspects, it is the composites are being machined. So you can tell what is the need of a non-conventional machining process. Hard to machine materials can be easily machined using unconventional machining process. That's why we are going with them. Right? For ECM also we have micro ECM also there. Micro EDM we have with the small tools. The purpose is in a hard to machine materials we want to put a minute holes, because in miniaturization we call it the word miniaturization. Okay, because you can see a watch. In this watch there are many mechanical elements. And nowadays it is what we are using is electronic type. But once you go with the mechanical watches, you can see many small products. That is called as miniaturizations. So in that cases, if I want to put a hole, then I can easily go on with this micro EDM or micro ECM likewise. Okay. Then machining of polymer matrix composites. So in machining of polymer matrix, the generally used machining process is the drilling. Right? So feed and speed are the two input parameters normally they will be using. Then drill geometry, point angle, the number of flutes, then helix angle we can change, diameter of the drill we can have, the material of the drill bit we can change. Okay, so these are the different parameters that we can include in that. Right? Then what are the outputs that we are going to study? So cutting forces is of two types in drilling. One is the torque. Torque is nothing but the twisting force, the rotating force that is needed to rotate the tool. Okay. Then the thrust force, the force that is applied against the cutting tool. The pushing of cutting tool, no? I'm going to push the cutting tool by using feed rate. So the opposite force that is being generated is called as the thrust force. Then surface roughness, the residual strength. If it is a polymer, then we can go with the delamination factors. If I'm going to use the fibers, okay, then I can go with the cylindricity error, circularity error. Okay, so likewise we can study many things. So these are the effect of different fiber attributes. So the fiber by fiber length, fiber diameter. Okay, so what type of fiber that we are going to use? Okay, if I am going to use a high strength fibers, then it will be also abrasive. E-glass fibers, we will be using glass fibers. So glass fibers will be of a higher strength, but it is abrasive in nature. So if I am going to use high strength fibers, then the abrasiveness of these will be higher. So obviously a higher tool wear will be there. If the tool wear is higher, the surface toughness will be higher. Then fiber diameter, the tensile strength reduces with the diameter, but the cutting forces will be getting increased. The cutting forces will be getting increased. Okay. If the fiber diameter is higher, the quantity of resin, whatever it is, the matrix material will be less. So in that cases, the tensile strength will be reduced, right? But higher amount of cutting forces is required to fracture that fiber, right? So volume of fibers, if I'm going to have a high volume of fibers, then the machining will be little bit difficult, because delamination or fiber pull out, fiber shearing will be, everything will be there. So if volume of fibers and the fiber abrasiveness is higher, then it is very tough. Okay. So the machining challenges that what we will be having is the delamination, first thing, then fiber pull out, then uncut fibers, then fiber breakout. So this affects the surface quality. But delamination is surface breakage. Then tool wear, because of the abrasive nature of the fibers, rapid tool wear will be there. If the tool wear is higher, then the machining characteristics will be reduced in that cases. Then possibilities in machining polymer matrix composites. Conventional, we can go with anything, but in unconventional, we can go with the water jet machining or abrasive jet machining or abrasive water jet machining, then laser beam machining, electron beam machining, plasma arc, ultrasonic machining process. So these are the processes that can be used. We cannot go with the EDM or ECM because it requires, what is the basic thing that is needed for EDM and ECM?
Conductivity, sir.
Conductivity. So it is not conductivity. The polymers are non-conductive in nature, so we cannot use EDM because some positive or negative poles has to be considered as workpieces in that cases. Then drilling of polymer matrix composites. So here we are going with machining the carbon fiber reinforced polymer, that is epoxy composite with a carbide drill. You can see cryogenic cooling with 4 mm of drill bitter at the 6 mm of drill bitter. So dry, that is no cooling is provided in that cases, but in the second case cryogenic cooling is given. So here you can see the thrust force. The thrust force is less for the dry. Okay, with the 6 mm cryogenic, the thrust force required is higher, and it is going to increase with increase in feed rate. Then this is the delamination factor. So number of holes. Okay, with a single cutting tool I am going to use. So dry and cryogenic. With the dry machining, with the increased hole numbers, the delamination factor is less. But if I am going with the cryogenic, it is going to get increased. So in drilling of polymer matrix composites, the cryogenic cooling does not make any effect. So that is the finding that is given here. But whenever we are going to use this drilling of metal matrix composite, if I'm going to use this cryogenic cooling, then the outputs that what you are seeing here now, it will be reversed in that case. Then we are going with the feed rate, then average roughness. For dry, you can see the roughness is higher. For cryogenic, the roughness is less. But you can also see this is for example 0.12, this is 0.17. So only at a higher feed rate there is a vast difference. Right? In both these cases, this is the time. The same trend you can see, the same trend on between the root mean square and also the average. Average is RA and root mean square is RM. Okay. Then we are going into the abrasive water jet machining. So this is the new type of machining which uses abrasive particles. Normally we will be using garnets as the abrasive in abrasive water jet machining, or simply without any abrasive, you can use the high pressure water that is being focused on the material for cutting. So acrylic cutting and all they are going to do with this only. Profile cutting on any polymers that is being done using this water jet machining. So nowadays, even this metal matrix composite, we are going to machine or cut using this abrasive water jet machining process. So the first one is the standoff difference. The standoff difference is nothing but the distance between the workpiece and the nozzle. If the nozzle and the workpiece difference increases, the MRR tends to increase. So the standoff difference has to be higher. So that higher MRR is being obtained. Then work pressure. What is the pressure with which the abrasive particles along with the water is being focused? For 150 you can see higher MRR. Okay. Then we have the nozzle speed, the speed, right? The speed increase in speed, obviously you know the MRR is going to get increased. Then abrasive grain sizes. Whenever I am going to increase the abrasive grain size, then obviously the MRR tends to lower, because the finer the particles, the cutting ability will be good. Am I right or wrong? Right? So you can see a simple example I will tell. Carpenters used to sharpen their tools using small fine sands, whether they are using any gravels or sand particles. So small fine particles tend to increase the MRR than the higher mesh sizes. Okay. So this is for the another cases. So surface roughness decreases with a higher SODs, the standoff difference. The standoff distance is higher. In this case, so this is the result that what I am presenting is of another people result. So he has provided that with increase in standoff distance, the mean SR, the surface roughness, is going to be lower. And this is also the case for nozzle speed is going to be higher. So here you can see the water pressure. With the reduced water pressure, increased water pressure, the surface roughness is good, because good machinability can be achieved. Good machinability can be achieved. Then size. If the size is higher, higher material, here you can see higher materials removed. If higher materials removed, then obviously the surface roughness will be higher in this case. But you can see the difference, 0.122, here 0.112, that's all. So that's microns only. So that's not a very bad surface roughness at all. So this is the case of machining time. So the machining time will be higher for moderate values. So that is what he has provided. With workpiece pressure, with a higher pressure, the machining time is going to be higher. Then the nozzle speed, the less nozzle speed, the machining time is higher. But with moderate speeds, the machining time is lower. So machining time increases with the higher abrasive grain size. So I am going to choose lesser abrasive grain size. So that is my aim. So I have to select this. I have to select this. So water pressure has to be normal and the nozzle speed has to be moderate. So this is the case. Then we move on to the micro and nano machinings. So in MEMS, nowadays we are going to come across two important terms. With this I will finish now. MEMS and NEMS, micro electromechanical system and nano electromechanical system. So these are the part of the miniaturization of metallic structures. So as I told, in a watch you can see number of mechanical rotating parts. So that are being developed by this MEMS and all. Nowadays we are going to move towards nanotechnology. In the nanotechnology, we are going to produce components with the nano robots you might be hearing of. So that components are being made by NEMS, nano electromechanical systems. So that are the two emerging technologies that we are going to have. Even nano robots are sent into our bloodstream. You can see that the small injector robots will be traveling through our bloodstreams, and it will be removing the blood clots or the lipid accumulations. The lipid is nothing but a fat accumulations and all no, on blood arteries. So that and all it will be removing, or it will put a injection, deliver. For example, it can deliver medicines at the particular places. So these nano robots injected into the bloodstreams will have much importance in targeting the cancer cells. So that is being proved. So miniaturization of medical tools is an effective method, right? So this is a top-down approach. So what is the top-down? From bulk material to small materials. So top to bottom approach. Top-down approach. We call it as top-down approach, right? So what is the need for miniaturization? So minimizing energy and materials that is used in manufacturing. Then precision and accuracy is another thing. Then reduction of powers. Then faster devices, right? Then increase the selectivity and sensitivity. That's the another thing. Then increase the accuracy and reliability. That is the case. Then it can be integrated with the electronics, simplifying systems. So you can see nanomites in a Hollywood film. You can see nanomites. I have forgotten that name of the film. Nanomites. Okay, they will be targeting the enemy, and they will be making it into zero. Within minutes, they can eat everything, or they can corrode everything. Even big structures, they will corrode like anything. So it can be integrated with the electronics, likewise. So these are the different micro machining studies based on the energies that is being used. So this is a traditional one, and this is the non-traditional one. So micro turning, micro milling. So you can see in a number of papers coming across these things. So micro drilling using small drill bits. So the conventional machines cannot be used. For this, we have to use only specialized machine or advanced machines. So in this micro abrasive jet machining, ultrasonic machining, abrasive water jet machinings. Okay. So MRAF technique, that is one more thing. Magnetic rheological fluids. Okay, MRF, magnetic rheological fluid, I think so. Okay, so then coming on to the thermal methods, so everything is going to be having the micron size. Okay, that is micron sized particulates are being removed from the material so that the surface finish will also be good. So in that cases, we cannot use for bulk materials. For bulk materials, we can directly go to traditional normal machining. For specialized applications only, we have to go with this. For miniaturization components. Okay. So with this, we come to the end of this today's presentation. And today, I have completed within the stipulated time periods. And I thank you all for your patient hearing for the 3 sessions. If you have any queries, you can ask me now.
Sir, I am Dr. Ramgopal Reddy from RVR. Sir, how these tool angles so it influences this machining of composites, sir, rake angles and all these things?
So normally we will be going with the relief angle, sir, because rack angle only the tool with the chip will be sliding over the rack face.
Yeah.
Right, but the relief angle and side cutting edge angle will be in contact with the workpieces. So if I am going to provide some relief, only the cutting edge will be in contact with the tool. But providing over relief will reduce the strength of the cutting edge and it will be easily chipped out. So maximum of 3 degrees, it will be good for you to have a relief angle. Okay. Because my research is towards that relief angle only, sir.
Okay, okay. Thank you, sir.
Thank you, sir. Thank you, sir.
Very good morning, sir. Senthi, sir.
Good morning, Pradeep, sir. Good morning.
How are you, sir?
Fine, sir. Fine, sir. Thank you. How are you doing, sir?
Yeah, very fine, sir. So nice presentation, sir, as usual. But I'd like to ask some questions regarding this machining of this composite materials. So,
yes, sir. Definitely, sir.
Sir, first of all, I would like to ask which is the best candidate, or you can say which is the best tool for cutting this in MMC? Is it PCD?
So it all depends upon what type of reinforcement that you are going to have.
So normally we have the ceramic materials like
ceramic materials also. There is a vast difference between SiC and B4C and tungsten carbide.
Correct, sir.
Because straight away, if I am going for diamond, you can look at the costs associated with that. So what we suggest is, we'll go with coated cemented carbide initially.
Okay.
The coating will resist the wear.
Right, sir. Correct, sir.
The coated cemented carbides is less in cost.
But sir, with the help of this coated carbide, can we achieve the higher cutting speed or? No.
If I want higher cutting speeds, then I have to go with the CERMATs and the PCD.
PCBN or PCBN is a good candidate, I think so.
CERMATs are a cubic boron nitride or a PCD only we have to go.
Correct, sir. Correct.
Otherwise, it will be very difficult. to
But
give
sir,
the lowest tool wear and the highest surface finish.
right, sir. But sir, most of the in the literature I have seen the PCD is being used for machining of this one. Although it's have some lesser toughness. So is it okay to use this PCD material for machining of these kinds of material? Like this?
Definitely, sir, because I am going to do the machining.
Yeah, yes, sir. I'm also.
The PCD is costlier actually.
Yeah, that is very much
It's not
costly,
chip out easily.
Yes, sir.
But the problem is, once it has been chipped out, you will be losing 15,000 rupees or 10,000 rupees, whatever it is. It all depends upon the type of maker that you are going to purchase.
Correct, sir. Correct. It is.
That's why economically feasible. We have to start with the coated inserts, then we have to move with cermets. That's why in research, normally we have to choose an uncoated one, then coated one, then another tool like cermets or CBN, BCN, so that a composite statement can be given.
That is right, sir. Actually, but the main concern is that if I'm using this only carbide or coated carbide, but that they will not give the higher cutting speed. That's why I'm using.
Yes, sir. Yes, sir.
This is the
but
main
our
problem.
aim is to achieve lesser tool wear and good surface finish.
Right, sir.
But in industries, normally they will be going with the diamond.
Okay.
Only for research, we are searching for different tools. But they will be going with the diamond tool, sir.
One thing I want to ask, sir, that is, what is the cutting condition? Whether we use this ampule system or we go for dry cutting. So which one is best, sir? Can you?
Sir, the purpose of cooling is to reduce the friction between the cutting tool and workpiece, and also to remove the heat at the interface.
That is right, but sir,
that is the main thing. But in some cases, what happens is at the tool interfaces, the coolant will not be supplied. So for this purpose only, we are going with the mist cooling.
But sir, may I? But in many paper, I have seen that by using the coolants, the wear is increasing, and they showing their result that wear is increasing.
No. If I am going to use, that's why I am telling. If I am going to supply the mist cooling with a high pressure, then the interfaces will not be cooled. So we have to consider an optimum pressure for mist cooling. And nowadays they have transformed towards cryogenic cooling. The results that what they are obtaining from the cryogenic cooling is really good.
Correct, sir. Correct.
But apart from this, the setup and all, it will take time. And also it is a health hazardous one. So they will be considering it off late.
Okay. And sir, and the last question is, sir, I'm asking about this fiber reinforced FRP. So can we reduce this pull out of these fibers and all these things using drilling machines? So
no, sir, we cannot reduce, because if I want this strength, so for machining is the final category. First, what we'll be doing is I want high strength materials. If I want to have a high strength materials, the fiber that what we are considering will also could be high properties. If the high property of PMC, polymer matrix composite, is achieved, then the fiber pullout will be there. Definitely there will be pullout or breakout will be there during machining. You can see the same micrographs of that drilled hole. No, you can see many fiber pullouts, fiber breakage will be there. That is a very important study.
Okay, sir. So thanks a lot, sir. Really nice lecture and a very well presented and explained. Really, sir. Thank you very much.
Thank you very much, Praveen, sir. Thank you.